Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fizi. I'll be tell about the Beet design filter and notch design filter. So, a Beet design filter is a type digital filter that is designed using a specific transfer function known as a biquadratic function. This transfer function is made up of a combination of second order section which are used to archive a desired frequency response for the filter. Because filters are widely used in signal processing applications such as audio and speech processing, where they are used to move unwanted noise or and change specific frequencies. The Piquet filter designs process usually involves selecting the appropriate filter such as type low pass, high pass, band pass, determining the cutoff frequency or frequencies, and calculating the filter coefficients using a technique such as the bilinear transform or the impulse invariance method. For the notch design filter, a notch filter, also as known as a bandstop filter, is a type of a filter is designed to reject a specified frequency or range of the frequency while passing all other frequencies. The design of a notch filter involves determining the center frequency of the notch and the bandwidth of the rejected frequencies. There are several methods for design notch filter, including analog and digital technique. For the analog notch filter, design involves using passive or active components such as resistors, capacitors, and inductors to create filter circuits that reject the desired frequency or range of the frequency. Um, Common analog notch filter topologies included twin T, multiple feedback, and active notch filter. Digital notch filter design involve using a digital signal processing technique to create a filter that reject the desired frequency or range of the frequency. Common digital notch filter types include infinite impulse response (IIR) filter, and infinite input response (FIR) filter. So the design process typically involves determining the center frequency and bandwidth of the notch, and then calculating the filter coefficient using the technique such as bilinear transform or the impulse invariance method. Uh, it is worth noting that notch filter can be used in a different field such as audio and speech processing, control system, and medical imaging, and it also used to suppress unwanted interface signal. So that's all for me. Thank you.
So next is synopsis and theory. The goal of filtering is to perform a frequency-dependent alteration of a signal. In many systems, filters are used to remove noise from a signal. So as we can see here, we can see that noisy is before filter and then for the clean is after filter. So next is what is filter. A filter is a device or a process that removes certain element or feature from a dataset. Filter can be used in a wide variety of applications such as signal processing, image processing, and data analysis. They can be used to remove noise, enhance feature, or extract specific information from dataset. There are many different types of filters such as low pass filter, high pass filter, band pass filter, and band stop filter. Each type of filter has their own specific characteristics and uses. Filter design. Filter design is the process of creating a filter that meets specific requirements for a given application. The process involves selecting the appropriate filter type, determining the cutoff frequencies, and then calculating the filter coefficient. The filter design process can be analog or digital. In analog filter design, the filter is implemented using analog components such as resistors, capacitors, and inductors. The most common type of analog filter are low pass, high pass, band pass, and band stop filter. The design process typically involves selecting the appropriate filter topology, determining the cut-off frequency, and then calculating the component value using techniques such as Butterworth or Chebyshev filter design methods. In digital filter design, the filter is implemented using digital signal processing techniques. The most common type of digital filter are finite impulse response and infinite impulse response filter. The design process typically involves selecting the appropriate filter type, determine the cut-off frequency, and then calculate the filter coefficient using techniques such as bilinear transform or impulse invariance method. In either case, the filter design process is iterative and the filter characteristics are often modeled and simulated before the final implementation.
Assalamualaikum. My name is Lukman Nur Hakim bin Abdul Razak. So today I want to explain about Lab 5 filter design and application by using filter realization wizard. Okay, this is our circuit. So we use mystery signal 2.avi, and for the hertz is 22,050 hertz, and for bit is 16 bit and mono. And we use two spectrum analyzer and spectrum analyzer 1. And switch, uh, the function for switch is to connect the direct signal and filter signal. And this is the filter. We use filter realization wizard. And lastly, we use audio device writer. So after we run, we can simply switch from raw signal and filter signal. So now I want to show you the spectrum analyzer result. So this is spectrum analyzer result for direct signal. Now, and this is the spectrum analyzer one result. For this one is for filter signal, and my friend will demonstrate to you. So that's all from me. Thank you.
So good afternoon, Sir Jamil. My name is Liu Dingfu and my reference number is B08201098. In this video, I'm going to present you about the demonstration of the original section of the lab 5. As you know, previously we are using the lab 5 as our title of the assignment. So this is the circuit for the lab 5 filter design. We are using the filter realization wizard to create a filter which we can use to filtering the signal, the input signal. Firstly, we are going to open and click here for setting. For setting for the variable of our signal, we are creating a linear low pass filter, which is also called as IR filter. Low pass, medium. Our sampling frequency is following as our input signal is 22.05K, and our pass band frequency will be 7500. Our stop band is about 840. So after we have design filter, and at the figure below, it will be a low pass figure waveform. So next is about to realize the model, okay, about the build model. After confirm everything is okay, we realize the model. So after all, a filter will be created. conversion, you can check. You can double click the filter to check the circuit of our filter. This is the circuit of our filter. So after all is done, you run the circuit. As you can see that our input signal is a high pass, which is a conversion between the noise and the another source input signal. So after filtering, this is the signal after the filtering, which is the low pass. Because as following by the theory that the filter is allow the signal passing through by the between the range of the cut-off frequency, which is our cut-off frequency is about between the range of our cut-off frequency is about between 7.5 kHz and 8 kHz. So you can see here after the 7 kHz, the frequency has been the frequency is splitting, which means the noise frequency is being reduced. So that's all from me. Thank you very much.
Hi, hi, Assalamualaikum. Today I'm going to present our project. Our project is our improvement from our lab 5. So here we use the audio 2, and this is our design for our filter. Here our filter design, we use low pass, high IR butterworth, and for the for the FS we use 22050, and for the FC we use 7350. This is the filter design. So here we hear the audio without filter first. This is the audio without filter.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
There are too much noise interrupt the man talking, so we are mostly only hear the noise here and here. So our filter design will create to reduce the noise. After we use the filter design, hear the sound.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Yeah. Okay, here our filter will not remove the noise, did not remove totally the noise, but it reduce the noise so we can hear the voice clearly. And here, why we don't remove it totally, it still have on here, and here the noise. That's all from me. Thank you.
Okay, for this part, we are going to remove the noise from this file, that is mystery signal to file audio. Okay, we are going to use filter design to remove the noise, and the specification for filter design we are using is the response type that we are using is band stop with IIR Butterworth design method. The frequency specification we are using is for frequency sampling is 22050. The frequency cutoff we are going to cut at 7350 and 11025. So this is the magnitude response that going to happen in this digital filter design. Okay, let's hear the audio for the original sound first.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Okay, as we can hear that there is so many noise in the audio. So this is the original signal that we get in the audio, and this is after filter. As we can see, it does use a band stop design, so it cut off the frequency perfectly at 7350 and 11025. So this is the band stop that happened after filter from the original signal. For time scope, we can see that this is the original noise that happened in the audio. We cannot see the main voice amplitude because it is covered with the noise. For the second one, the blue one, this is the after filter amplitude. As we can see, this is the amplitude of the man that is talking, and this is the separation of the between the two noise, between the sound and the noise. Okay, let's hear the after filter sound.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Okay, as we can hear that there is no noise in the after filter sound because we are using the band stop with the specification that I just showed. Okay, this is the end. Thank you.
Greeting to everyone. My name is Vaibhishri Chandaras. Now I am going to explain about our conclusion. We can see that notch filter is more suitable to use than a bicode filter. Notch filters are used to remove a single frequency or a narrow band of frequencies. In audio system, a notch filter can be used to remove interfacing frequencies. The notch that is being produced by bicode filter still remain at the same as the input. In the block parameter of digital filter first, the response type was set as low pass and value according to procedure. The result before the digital filter was exactly same as result of the signal before the signal passed through bicode filter. Before the signal passes the filter, the signal gives out low frequency followed by band pass frequency and continue with high frequency. After the filter, the unwanted frequencies were removed and given out according to the filter we use as shown in spectrum scope result. So that notch filter used in medical fields to implemented for evaluation of the distortion caused on ECG signal. That's all from me. Thank you.
Peace.